minus 0.0592 over N times not the natural log, but the regular log of Q. Now that seems kind of weird to go from natural log to log and all this stuff. The deriving of this equation from this equation takes an entire page of stuff. This is all how they do it. You don't need to be able to do that. You just need to be able to plug in what Q values are, what electric potential values are. So we'll use that in our next example. So we good? Do you have all the equations written down? N here represents the same thing, the number of moles of electrons that you need to cancel out for the half reactions. Okay. All right, this one's going to be at 25 degrees Celsius. And just for saving room, I'm going to write the equation on top. We're going to have VO2 with a plus charge plus zinc, solid zinc, giving me zinc ion, zinc 2 plus. That's the normal charge of a zinc ion. And then VO with the positive 2 charge. And I'm going to be given different concentrations of these things. So instead of, if we were to calculate the standard electric potential for the cell, then all of these concentrations of ions would be 1 molar concentrations. But now we're going to have different concentrations, so it's going to change. We'll have a 2 molar concentration of those ions. Zinc doesn't matter because it's not part of the equilibrium expression. It's a solid, so doesn't matter. It's there. It's not a solution. Zinc ions, 0.10 molar. And then VO with a plus 2 charge, 1 times 10 to the negative 2 molar. And then I'm also going to be given information that the concentration of hydrogen ions is 0.50 molar. Okay, and I'll need that. Before I can go and use the equation and solve for the electric potential, I need to figure out what the standard electric potential should be if all the concentrations were 1, and then I need to go through and I need to figure out what Q is. So my first step is to figure out, first of all, separate them into half reactions. And so I'll start with my VO2 with a positive charge, that turning into VO with the plus 2 charge. Now, kind of a shortcut for you, you could go through this and balance it, on your own with waters and hydrogens and electrons and all that stuff. But if you find it on your reduction potential chart, it's right here, it actually shows the balanced format for you. So then you can just copy it down exactly like this. I need to have 2 hydrogens and an electron on the left and then a water on the right. So I'll put my water here, and how many? 2 hydrogens, 1 electron. And I was given electric potential just from the chart was 1.0. Okay, then I need to look up the other half reaction is zinc to plus. And then this one's easy, plus 2 electrons right there. Looking that up, and then I need to flip it because it's right here. Zinc 2 plus 2 electrons, but I have it going the other way, so I need to flip my electric potential here to be 0.76 volts. Okay, now I can figure out, these are standard, by the way. I am bad at putting that there, but I shouldn't be because we don't want to confuse the two. All right, so my standard electric potential, if all of the concentrations were 1 molar, my electric potential for that cell would be 1.76 volts. Okay, so I'll need that. But I also need Q, and to figure out Q, I need to do it like I would calculate equilibrium constant, so I have to do products over reactants. So I have to figure out what the products are and what the reactants are. So I've got to figure out this overall balanced equation here. This one, I need to multiply by 2, right? So that I can cancel out my electrons, okay? Now, that'll give me, when I do that, I'll have 4H plus 2VO2 plus zinc gives me zinc 2 plus 2VO with a positive charge. I have to say that carefully, otherwise they sound the same. And then, plus 2 plus charge, plus 2H2O. So then, to calculate Q, it's products over reactants. So let me go with my products over here. I need my zinc, my concentration of zinc, multiplied by my concentration of VO with the 2 plus charge. That has to get squared over my reactants, H plus concentration. That's why I needed to be given that information at the beginning, to the 4th power, and then VO2 with the positive charge squared. Okay, I can plug in all my concentrations that I was given initially in the problem. So zinc was 0.10 molar. VO2 plus was 1 times 10 to the negative 2, and that was squared, over my hydrogen concentration, that was 0.50. That's to the 4th. And VO2 plus, which was 2 molar, and that gets squared. Okay, gives me a Q value of 4.0 times 10 to the negative 5. Okay, so these numbers are the ones I need to calculate my electric potential. That's Q, and then my standard electric potential there. So then I can go ahead and just plug in E equals my standard electric potential, which was 1.76 minus 0.0592 over 2, because I canceled out 2 electrons, so that's the N number, times the log of my Q and I get 1.89 volts, and that's the final answer. What you want to compare then would be, this is the electric potential at the conditions that I was given, the concentrations that I was given. This would have been the electric potential if I had 1 molar concentration of all the ions. And so you can see that the voltage, I've got more voltage than I did at 1 molar concentration. And you can think about that is on your reactant side, these numbers of concentration, I had 2 molar and 0.5 molar, are bigger numbers than the ones over here on the right. And so if you think about it, Le Chatelier's, that it's going to shift to the right because they have more reactants. And so because it's shifting to the right, it's going to be producing more voltage. All right, so far we have been dealing with different half reactions in the different cells and then figuring out electric potential. But now there are these things called concentration cells, where instead of the half reactions being different, they actually happen to be the same half reaction, but now it's the concentration of the ions that are different in each compartment. I'm going to draw another little diagram in there. Okay, here's what this looks like. I'll draw my different cells over here again. And before, you know, we would have like a copper electrode and a zinc electrode or some kind of metal. But now they're both going to be the same. So let's just say that I've got a silver electrode over here and another silver electrode over here. And they're connected. And I've got a voltmeter in there to show my voltage. And there would be some kind of salt bridge or porous disc in the middle to kind of keep that flow of electrons going. And in my solution, maybe I dump in silver nitrate or something, just because nitrates are always soluble, right? So I would have silver ions in here, silver ions in here. It's like the same, I've got the same thing going on. So how does this produce any kind of voltage? Well, the difference here, the key thing here is the concentration. So maybe on this side, I have 0.10 molar concentration of silver ions. And over in this cell, I've got 1.0 molar concentration of silver ions. So in one of these cells, I'm going to have silver ions plus an electron giving me silver. Oops. In the other one, it's going to be the opposite. I'm going to have my silver turning into silver ions plus electrons. So I've got to figure out which direction the flow of electrons is going to be. And here's kind of the easiest way to figure it out. Is this little statement down here. Electrons are going to flow in the direction that will equalize the concentration of ions. And I'm talking about concentration of silver ions here. And so if I think about it, first of all, on the left, I have a smaller concentration of silver ions. Okay, so this side is going to want to try and make more silver ions. So in order to make more silver ions, it's going to have to, from the silver here, give away some more electrons so that I'm left over with extra silver ions. Does that make sense? Draw. So because they want to equalize concentration of ions here, and I've got less silver here, this side is going to give up electrons so that it's going to increase my amount of silver ions there. And so just by definition, I know that electrons flow from the anode to the cathode. You can maybe think of anodes as being like anions, or the negative side that's giving up electrons. Cathodes, like cations, that'd be gaining the electrons. Okay? And then just thinking about an ox and red cat, I can figure out here that this equation goes with my cathode because it's being reduced, red cat. This equation goes with my anode because it's being oxidized. And what else about that? If I look up these half reactions, is it on yours? Here we go. If I look up these half reactions, silver plus an electron gives me silver. It's 0.8, so this would be 0.8 volts. If this were the same exact concentration, then this would be negative 0.8 volts and I would have 0, right? But since I have different concentrations, I do have this slight flow of electrons, and so I am going to get a positive voltage reading here. And you need to be able to, or you need to figure out what that voltage reading is using the Nernst equation. So E naught, which would be my standard electric potential, which for this one would be 0 when you have these concentration cells. Because if they were the same concentration, there would be no flow of electrons. minus 0.0592 over n. In this case, there was one electron there that canceled, so that's my n number, times the log of, now Q, which is products over reactants, and if I went through and I, summed these up, my products, I'd have silver ions over silver ions. Okay, so how do you know which concentration to plug in where? Just as a general rule, the bottom number is the bigger number. Okay, so this one would be the smaller concentration number. So I would plug in 0.10 over 1.0. And you get, this gives you 0.0592 actually, volts. Okay, so the numbers are very small, but you do get a slight flow of electrons and voltage reading when you have differing concentrations of solutions in each side of the half cells. Okay, questions on that? I've got one more small thing, and then we'll be done. I don't know why this is all empty. We don't need that. Actually, yes, real quickly about batteries, and then we need to talk about oxidizing capabilities. Like, you'll be given a list of things, and it'll say which one is the better oxidizing agent. So you need to be able to figure out which one that is. We've been drawing all these galvanic cells with the two half reactions and showing the flow of electrons and figuring out electric potentials. But whenever we figure out the electric potential of each one of those little systems, you almost never get anything more than just like a couple volts, 1.5 volts, less than a volt. Okay, but we have batteries that are 1.5 volts. We have batteries that are 6 volts, 9 volts, 12 volt batteries. So how that happens is you can't just have two half reactions, one galvanic cell that's going to produce that many volts. And so what they do is they just take several cells and they hook them up together in series and the voltages add up. So that's how you get higher voltage batteries. Now, oxidizing capabilities, I just have two quick examples. The first one is you will be asked a question like, is iron 2 plus capable of reducing VO2 plus? If iron is going to be reducing VO2 plus, then that means itself iron is going to be oxidized, which means that it's going to be going from Fe2 plus, it's going to be increasing in charge, to like Fe3 plus. I'm going to look up on my reduction potential chart the one that gives me this, which it might not be, maybe it's on the one in your book. See if you can find it. Okay, there it is. It's 0.77 volts, but it's written opposite of this with the Fe3 plus on the other side. So I need to flip it and make it negative. So it's negative 0.77 volts. And for this one, just figuring out if it's capable of reducing, you don't have to write out the full equation and all that. All we're going to be concerned about here is the standard reduction potentials and what they add up to be. So just make sure that if you have to flip it, that you flip the sign over here. So then if VO2 or VO2 plus is going to be reduced to maybe VO plus, and I could spend forever looking on the chart for it again, or you can just trust me. And I already looked it up. It's 0.34 volts for that reduction potential. So then when these add together, I get a negative answer. I get negative 0.43 volts. Do you think that that's going to happen if the overall thing is negative? No, it's not going to happen, okay? So it's not capable of reducing that. You have to get the combination to be a positive voltage number in order for it to be a possible combination of half reactions that can work together to produce a positive voltage. Okay, next type of question. Any questions there? Next type of question would be, which one is the strongest oxidizing agent? Okay, which means that it's being reduced. And then the question is, well, would it be magnesium? We'll forget this number 1 here. Magnesium, would that be the strongest oxidizing agent? Would iron be the strongest oxidizing agent? Or, this is called like cerium or something like that. Was that the strongest oxidizing agent? If it's an oxidizing agent, that means it's being reduced. So this one would go to Mg, magnesium. This one would go to Fe2 plus. This one would go to Ce3 plus. And I would get electric potentials for these. This one's 2.37. This one is 0.77 and 1.70. Can't find that one. And then the question is, which one would be the stronger oxidizing agent? You pick the one with the biggest number. So this one would be the strongest oxidizing agent, this one would be the second, and this one would be the third. Okay, so the largest electric potential would be the greater oxidizing agent. That's it. I'm done. Okay, your assignment today is page 832, and you have lots of time to begin. 43, 45, 51, 53, 55, 65, 71. That's it. Start it today so that you get a lot of it done, so that you don't have to do so much for homework, because tomorrow we have our study session at 1 o'clock. I'll give you guys a practice test to work on during that time tomorrow.